This video discusses time domain reflectometry. Cable problems. Metallic cables used in an electronic communication system can develop problems that affect their performance. Cable problems are from chemical erosion at cross-connect points, especially those that are exposed to air, and mechanical failure due to pulling and pushing of the cables. Time domain reflectometry. Time domain reflectometry is a technique that can be used to locate impairments in a metallic cable within a few meters, up to a distance of 30 kilometers, depending upon the strength of the generated pulse and the attenuation of the cables. This makes use of the well-established theory that transmission line impairments such as shorts and opens cause a portion of the incident signal to return to the source. Time domain reflectometry. This is used to determine the length of the transmission line and the amount of load mismatch. So as you can see in the example on the left, amplitude is plotted against time. Initially, there is one transmitted pulse. This is usually from a function generator or a pulse generator. It will travel down the transmission line, and then the oscilloscope will listen if there will be a pulse returned to the originating source. So in this case, the transmitted pulse is, of course, a lot higher in amplitude than the reflected pulse. So we just need to measure the elapsed time. But a problem arises when the transmitted pulse is too long. As you can see in the second example, the transmitted pulse is too long. The reflected pulse has already been detected, but the transmitted pulse has not completely finished sending yet. So during this time, we cannot measure the elapsed time. So all we need to do is to measure the elapsed time using the oscilloscope, and we will apply this formula. The distance between the impairment and the source would be D is equal to V times T divided by 2, wherein D is the distance to the discontinuity as measured from the source. V is the actual velocity in meters per second. K is the velocity factor. We'll use this to compute for the velocity of the signal in the transmission line. Ideally, it is equivalent to the speed of light, but of course, the speed will be lower in real life scenarios. And then lastly, T is the elapsed time in seconds. So this is the setup when we try to connect the pulse generator with the oscilloscope together with the transmission line. So as you can see, the pulse generator will send a pulse, which will then be recorded in the oscilloscope, and it will also travel down the line since the line and the oscilloscope are in parallel. So the pulse will also travel down the transmission line because it is connected in parallel with the oscilloscope. If there is a discontinuity in the transmission line, a portion of the first pulse will be reflected back and it will be recorded in the oscilloscope. So we can actually measure the time from the first pulse up to the second pulse. And that is what we need for our formula. Now, we have to ensure that the source impedance and the transmission line impedance, or the characteristic impedance of the transmission line, is equal. And the only discontinuity that we'll be measuring is the discontinuity in the transmission line or in the load. And this is an actual test setup for time domain reflectometry. As you can see, the pulse generator is connected in a T junction. So the pulse generator, the transmission line, and the oscilloscope are all connected together. Now we have to make sure that the connection of the pulse generator and the oscilloscope are as close as possible. And of course, we have to make sure that the connectors do not have any kind of impurities or corrosion in them so that we can ensure a perfect match. Now this is what it will look like if the characteristic impedance of the transmission line is equal to the impedance of the load. As you can see, there is no reflection, or there is no pulse reflection in this case. The only thing we can see in the oscilloscope are the pulses from our pulse generator. And this time, the load impedance is not matched to our transmission line impedance. So in the first case, on the left, we can see that the load impedance is less than the characteristic impedance of the transmission line. So we can see this waveform in our oscilloscope. And the second case, this is the waveform when the load impedance is higher than the characteristic impedance of the line. So upon observing the waveforms on the oscilloscope, we can determine if the load impedance is greater than or less than the characteristic impedance. And this is a perfectly mismatched line. In the first example, we have our load equal to a short circuit, 0 ohms. So this is a transmission line that is terminated by a short circuit. So this will be the waveform that will be displayed in the oscilloscope. And in the second example, this is a transmission line terminated by an open circuit. So we can also determine if the transmission line is terminated in an open circuit or in a short circuit. Next, if the load is not purely resistive, so there are capacitive and inductive reactances, we can also determine the impedance from the oscilloscope. So when the load is not purely resistive and there is a capacitive reactance present, and the load will have this kind of oscilloscope display on our left side. And on our right side, we can see that this is the oscilloscope display if there are inductive reactances. Let's take a look at this example so we can apply our formula. A pulse is transmitted down a cable that has a velocity of propagation of 0.8 times the speed of light. The reflected signal is received 1 microsecond later after the original pulse is sent. Now the question is, how far down the cable is the impairment? So of course, we're going to use this formula for our TDR, time domain reflectometry. The distance from the source to the impairment is equal to the velocity of the signal times the time difference between the first signal and the reflected signal divided by 2. Never forget the divided by 2. So let's plug in all the given into our equation. So we have d, the distance, is equal to 0.8 times the speed of light times 1 microsecond divided by 2. And then we calculate that, we'll have our answer. The distance is equal to 120 meters. So from the source, we'll measure 120 meters and we can detect where in the cable is the impairment.